Good morning, everyone. Today we are going to continue our discussion on Aurelian graphs. Okay. Today we focus on applications. So last week we discussed characterization of Aurelian graph, which can be characterized by a connected graph where every vertex has an even degree. All right. So what's the use of Aurelian graph? Actually, it has a lot of applications, some real-life applications. Today we'll discuss, I hope we have time to go over three of them. First one is called the Chinese postman problem. It's introduced by Chinese mathematician in 1960 called Guan Weigu. All right, and the second we are building a sequence of binary string with certain properties called the de Bruijn sequence. And third one will be related to a game called the light out game. You may have played with that game. All right. So let me briefly give an introduction of these three applications. In the Chinese postman problem, postman wants to deliver mail to certain street. So starting from his post office, he wants to cover certain street. So walk along to cover certain street. So that some certain street has to be covered at least once. For example, maybe want to deliver mail in this region. Maybe in this region. So maybe post office here. All right. The postman has to start somewhere here, maybe, then cover these streets. So this target to be covered. The problem is to find a closer walk. Of course, in order to deliver the mail efficiently, the postman wants to find a closer walk of minimum length. So that's the purpose or the objective of the walk. We need to find a closer walk that visit each street at least once. All right. So that's the problem of Chinese postman problem. A second problem is de Bruijn sequence. Look at the sequence of binary numbers 0 and 1. Do you notice anything? Actually, it's not easy to notice something special. This one has the property that all 16 different binary constraints, binary numbers with 4 bits can be obtained by this sequence. If you take consecutive ones, the first one gives us 0, second one gives us 1, so this gives 0, 1, then third one, this gives us 3, this one gives us 7. So actually, all binary numbers from 0 to 15 can be obtained from this sequence. And let me locate back, for example, this one. It's cyclic. 0, 1, 0, 0. So this gives us 4. So all 16 different binary numbers can be obtained by this from the sequence. Such a sequence called de Bruijn sequence. All right. A third one is this the line out game. So typically in a square board, so there's a chessboard in a square chessboard, and not rectangular chessboard. Some lights are on, some square lights are off. So when we push a button, then the light on that particular square will change from on to off and from off to on. For example, let's push this button, so this one will become off. Now, other than that, it's a 4 neighboring. So typically there are 4 neighboring squares. Lights of these 4 neighboring squares will also change. So then these 3 become on and this one become off. This lights out game. I will show you in a bit later, okay, when we discuss detail of this game. So that's a game, but actually there are intermediate connection between this light game and Aurelian graph. So we'll discuss that one. I hope I will have enough time. Right. So our main will concentrate on these 3 problems. Application, real life application. At least these are real life applications. Of course, this one is a real life application. Games, right? Play for fun, it's real life. All right. Okay. Of course, there are very simple applications which we are not getting to it. Of course, most simple applications are the following 2 applications. All right, look at this picture. I draw it with 3 strokes. The question is, can we draw it with 1 stroke without lifting pen? So draw in 1 stroke. Another one is polyhedral. I showed you last week. Give a polyhedral. No one. Look like. It's difficult to show on 2D. So this 3D looks like 3D. So there's something on the back. Okay, something on back. So there's something on back. So which we cannot see. Is it possible to travel along the edges of a polyhedral using 1 stroke? Again, it's a 1 stroke problem. Travel along the sides, edges of the polyhedral. And start at a point and come back. So can walk around along edges. So maybe then go to back and whatever. All right. So these 2 problems can be either solved by our CRM already on the graph. So this one, we can make it a graph, make this one a graph in very simple way. So here, these intersection points will be vertices. All right, here, these vertices will be vertices. The vertex of polyhedral will be vertex in graph. And we form a graph. Once we have a graph, the problem is really become the problem of time. The problem becomes problem find a walk that visits each edge exactly once. Exactly once, sorry, not one. Right? So this one may want us to return to the original position, then it's exactly R4 or radian 4 problem. That's why if we do not need to, I can start anywhere, finish anywhere. And in this case, I need, because I may start here and then eventually we'll finish here. Then start here and finish here, actually. All right. Then it's looking for, instead of Aurelian tool, we look for so-called Aurelian piece. Of course, these are trivial applications. We're not to discuss it. It's trivial, right? For you, it's very trivial, so easy. So all of you are super brain because you know how to solve this problem. All of you are super brain, right? So congratulations, you become super brain now. All right. So let's see. So that's one thing we haven't discussed. Make a connection between this one and this one. Then we'll get into these 3 applications. All right. In the sense of Aurelian graph, are 2 notions. One is connected, one is even. The Aurelian graph means connected, even graph. All right. So here, even refers to degree. So this one means a graph is even graph if every vertex has an even degree. The Aurelian graph is just an even graph that is connected. So that's characterization of Aurelian graph. Now we're going to make a connection between Aurelian graph and Aurelian piece. If we do not need to return to our starting vertex, then what we're looking for is called Aurelian piece. The only difference between Orleans 2 and the pass is in a pass, we do not need to return to a starting vertex. The other requirement is that we visit each edge exactly once. All right. The Aurelian graph is connected even graph. The difference between Aurelian graph and a graph with an Aurelian path, sorry, is EU. Aurelian path is this one allows exactly two order degree vertices. At most two order degree vertices. If we have Aurelian tool, then certainly we have Aurelian path. Okay, so that's why. Okay. So a graph that contains Aurelian paths, we need to set it and can at most two order degree vertices. Of course, these two order degree vertices will be starting point and end point. That's quite easy to see. All right. That's only difference. Of course, by handshaking theorem, at most two order degree vertices means either no order degree vertices or zero or two order degree vertices. It cannot be one. The handshaking theorem, because number of order degree vertices must be even. The graph contains either zero order degree vertices or two order degree vertices, then it will have an Aurelian path. So that's the connection between Aurelian graph and the graph containing Aurelian paths. Now, also there are connection between Aurelian paths or Aurelian cycles in diagrams. So for diagram, our graph has directions, edges has directions. So in this case, what will be a characterization for Aurelian pool in a diagram? So we may have a diagram. The graph may look like this. So that's a diagram. So actually from this one, it's easy to obtain a characterization of diagram that admits Aurelian tool. It's very easy to do it. So do you see it? What's the necessary and sufficient condition for diagram to contain an Euler tool? Of course, this one also holds. If it's not connected, of course. But to the case for diagram, connectivity can mean two different things. So here, what we mean is if we ignore direction of these edges, then it's connected. So that would be good enough. Another strong notion is a diagram is formally connected. If for any pair of vertices, they are passed from X to Y and also from Y to Z. So for diagram, that's different because we may have the case. So for this diagram, we have paths from X to Y, but we don't have paths from Y to Z. So that's kind of called a weak connectivity. Another notion is strong connectivity. So in this graph, we have paths from X to Y, also from Y to X. If when graph contains an Aurelian tool in a diagram, it's always strongly connected. But in the statement, weak connectivity will be good enough. So here, what is required is connected. Now, the condition for undirected graph is every vertex has even degree. So for my graph, what's the necessary and sufficient condition? Of course, degree will be even because one coming, one out. Now, one coming, one out, that means in degree will be same as out degree for every vertex. So that's a sufficient condition for Aurelian tool in a diagram. We can also talk about Aurelian points, which I will not discuss. It's easy to obtain it. And from here, from these, you can either obtain it by yourself. Actually, should put it into the homework. It's a good problem for homework. So for this graph, it's easy to see that. So this one in degree out, degree out is 2. 2 in, 2 out. So 1 in, 1 out, 2 in, 2 out, 2 in, 2 out. This one 3 in, 3 out. So this graph, I will get the Aurelian tool. Actually, when I draw this graph, I follow Aurelian tool when I draw this graph. Okay? So these are basic theory behind Aurelian graph. Now we are going to discuss our real applications of these 3 applications: Chinese postman, a divine sequence, and the light off, a light out or light off game. Okay. All right, Professor Dirk, any question about these fundamentals? If not, we're going to get into real business. It's not easy. Okay, especially the third application, light out game. It's not easy. The first 2 are relatively easy. Okay, and actually the first one is related to one of the homework problems. So I'm giving you a hint for homework problem. Okay, yeah, at least one, actually, maybe 2. Okay, I think perhaps 2 homework problems related to the next application, Chinese postman problem. All right, any questions? No? Okay, so we'll continue. Okay, so it's easy to formulate the problem by, well, it's very easy to see because street, we are dealing with street. So intersection will be vertices, and each street between 2 intersection will be an edge. All right. So we can talk about the problem on a graph. Okay, so let's look at this very simple graph. So the problem is to find the closed walk on this graph so as to minimize the total length of walk. And after the walk, contain at each edge at least once. All right, the two properties. One is visits each vertex or each edges. Now instead of exactly once, it's at least once. Because sometimes it's impossible to get exactly once. Namely, when the graph is Aurelian, we cannot do it. So we have to visit each edge at least once. Secondly, the walk must have minimum length. We want to minimize the length. Otherwise, it's very easy. If we don't care about length, of course, you can just walk on. All right. Now, this problem has a lot of have a lot of other forms instead of just postman. For example, we want to clean the street or spray water in the street, the infection of the lungs. All these problems can be formalized as this problem. So it's this version of a graph problem. Actually, the problem rarely has a lot of applications in practice. Okay. Now, one extreme case is a graph is the Aurelian graph. So in that case, it's easy. We know how to solve it. What we need is to find our tool, or Aurelian tool. The problem is when the graph is not Aurelian. So what do we do? For example, this one is not Aurelian graph. It's connected. Unfortunately, there are 2 vertices of odd degree. Here is 3, here 3. Maybe I add one more vertex here. to illustrate purpose of minimum length. So that's the reason I exist work. Otherwise, no need. All right. So how can we find a closure walk or minimum a closure walk or minimum length that gets each edge exact once? So let's just do an experiment first. Try to see how we can come up with a walk. All right. We can start anywhere. For example, we just start with this arbitrary vertex. Maybe okay. Then walk around. So we may do things like this. So far so good. So far so good. All right. Now we visit each edge once. Now the problem is I start here, but now I'm here. I have to return to here. So I visit each edge already. So in order to return here, I have to get some edge more than once. So here I have a choice. So in this particular case, there are three ways, exactly three ways. I can return to this point through this path or through this path. So if I through this part of this path, each will give us extra number of edges, three extra number of edges, three extra number of edges. If I return in this way or this way. Now, if I return in this way, it only gives me two extra number of edges. Actually, that's as possible. The total length for a closure walk in this class that gives each edge at least once, the total number of edges plus two. So this one is possible. All right. So what happens? At a certain point, I have to repeat edge more than once. Now look at edges formed by red one. So instead of drawing in blue, now I show the solution. Okay. Now I also draw it in red. So return here and here. Now if I draw the red graph, what I get? I get a multi-graph. Right? If I draw the red edge, what I get is this graph. This is a multi-graph. Now what can we say about this graph? This one is Aurelian. So with addition of this one, the graph becomes Aurelian. So really the problem is to add paths to the graph to make the graph Aurelian. So the problem becomes how we can add paths. Now it may have multiple edges, so it will become multi-graph. The problem is that how can we add edges to G to make a graph an Aurelian graph? And to minimize the length, we want these number of edges being added to be as small as possible. So there, the condition here is add edges with minimum total length. All right. So that's what we need to do. How can we do this? Remember, handshaking theorem, I'm not going to discuss the whole algorithm, okay, but we'll give you main idea. By handshaking theorem, number of order degree vertices will be even. The order vertices, there are even number of order vertices, so we can clear them up actually. So what happens is between every pair we add a pass. Eventually, that's what we get. So in order to solve this problem, we need something else called a matching. Minimum weight matching, which we will not discuss in this course, but I will give you the idea. So what happens is we add a minimum matching that's corresponding to these points. Once we add it to them, we get an Aurelian graph. Then we can find Aurelian graph. In the new graph, we solve the problem. Of course, in general, edges may have weight. So instead of this, edges may have weight. Maybe this weight 1 here, 2, 3. So there are 2 edges, maybe weighted high here, 9. So here maybe 3, 4, well, 1, 3. So then instead of adding this one, maybe best way is to add this pass. Instead of this one gives us total length. X length will be 13, but this one only 6. All right. Okay, so let's give you a basic idea of how we solve the Chinese Postman problem by converting the graph into an Aurelian graph, adding points. And there are 2 homework problems related to this one. So this one can be served as a hint for these 2 problems. One is special case when there are only 2 odd degree vertices. Then I want you to show that the path we add is the shortest path between these 2 vertices in order to minimize the length. It's kind of intuitive. This one is relatively simple. And last problem, I think is the problem 10 is also related to this one. All right. Okay, is that clear? The basic idea? Of course, we haven't discussed all the details because there's some detail here. Maybe in the algorithm course we'll discuss it, not for this discrete math course. Okay. All right. Any questions? No. Okay. Then we get into next application. Let me show you. Okay. Let me show you some picture first for next application. Your screen. Okay. Okay. Let's see. Which one? Tiles. Let's see. Quite a lot. Okay. So let me show you some. For example, this one. So the next application has something to do with how we indicate the location or position of a disk. So here the disk, one way to use numbers, so indicate its position. Here 1, 2, 3, 4, so 5, and so on. So that's one way we are doing it. So here, these pictures are showing the this thing. So you can see some. Let's see. This one not very good. Yeah, there are quite a few. The simplest one is the old style form, of course, from 0 to 10. So this shows the position, all right? So some are quite complicated, I think. Let's see. This is for civic use, so not very precise. Some for military use, maybe to, this one is a little bit better. You see, so we have 9, 90, 120, 80 degrees, so it shows 360 degrees, and so the minimum unit is a degree, 1 degree. So you can see. So in order to measure position of a disk, that's one way to do it. All right. Okay. So that's one way. Okay. So next one is a Debye sequence that has something to do with this positioning of a disk. How would we position? Tell the position of a disk. Oh, you want to ask me whether we introduce these things in algorithm course? Yes, when I discuss algorithm course, I will discuss the Aurelian cycle and Aurelian path again, but mainly on algorithmic part. How can we find such thing quickly? And maybe also as these application, how can we find the solve Chinese Postman problem quickly? How can we find the Debye sequence quickly? Maybe, okay, I'm not sure. But Chinese Postman, I guess most likely, but Debye sequence maybe not, because that will be enough. Today's material will be enough. So define sequence is related to how we can tell position of a disk. A disk normally is low pace. So how can we know the current position? For example, this position. How can we tell what is this current position? So one way is to use numbers to label it, as I showed you in the picture. But the precision, if I need, so if the precision is not high, 1 to 10, maybe it's not difficult. But if we need high precision, that's not easy at all. We can use numbers, say, like, let's see. All right. So if I only need to know 8 different positions, perhaps I can write number. For human, it's easier to see. But for machine, that already create a problem. How can a machine tell easily this one is 2, this one is 3, this one is 4? Not to mention if we have to divide it into many, many sections, for example, 100, and was only 1,000, or even bigger. So maybe for high precision, we need really many, many positions. This one even not good enough. Maybe 10 to 10s. Certainly, this way will not work. Actually, this one has a lot of application, even in high tech, maybe I mean really high tech, maybe in rocket or airplane, when we have really to control the position of a disk. For example, if I want this to precise control, if I want to locate this disk by maybe by, let's see, this much. For tiny location, how can I control it without under exact position? When, for example, for rockets, the positioning has to be very, very precise. When I locate the nodes, how can I know I'm in the right position? So this way certainly does not work. All right, so what else can we do? Let me show the clock. Sorry. I lose that one. Okay, can to close this window. Okay. All right. So what else can we do? The same idea comes from here. So basically, probably to mark the disk. The easiest way to mark the disk is maybe just use a binary thing to mark it. Maybe a dent, no dent or dent, dent here, dent, no dent, dent. So this dent maybe represents 0, no dent represents 1. 1, 0, maybe 1, 0, 1, 1, 0. Then it's very easy to mark it. Use a dent and no dent. So we can mark the whole disk by a sequence of bits of binary numbers. 2 bits, 0 and 1. So eventually for this, if we divide it into n sections, so that will give us n bit fit. Right? If we mark it in this way. So for example, for 4 numbers, if we mark it, a 4 bit of a length 4, is 4 numbers, we can mark it in this way. So that gives us 4 different binary numbers. In this case, they happen to give us here 0, 0, here 0, 1, here 3, here 2. So you happen to give us 4 different numbers. So if we have this situation, then we can use these numbers to tell the exact position of the disk. So that's the idea behind the blind sequence. How can we construct a sequence so that all consecutive with a string of given length, say k, give me a different number. All right. So that give us the following. maybe instead of using n, I use 2 to the power of n. So how can we arrange 2n theorem ones in a circle so that if I take any n consecutive ones, so take any n consecutive ones, that give me a string of length n. So I want all these strings to give me different binary numbers from 0 to 2n minus 1. So is it possible to arrange them in this fashion? Of course, for the physical application, in order to tell the precision, instead of use a single sensor, so here the sensor will be n sensors. So number of sensors should be n in order to tell that. All right, I'll show you a picture. I think I have got the picture from this. Let's see. I think I see one. Let's see, maybe. Okay, let me search again. I think I deleted it. Okay. Oh yeah, here it is. Okay, I found it. Okay, share screen with. Okay, so this one. So there are 4 sensors. Okay. So this is actual physical device. All right. Now the question is, how can we do it? Yeah. How can we do it? Is it possible? Of course, if I give you just 4 or 8 even, then it's not too difficult. For small one, you can try it out. Just as okay, so again, it's a hint for the homework coming for homework 5, not homework 5th homework. All right. Now I have to admit, these problems, some of them are very difficult. The most difficult part for graph theory part is you may have no idea where to start. So you really need to do a lot of exercise to get a feeling. The difficult part is you may have no idea where to start. Now, first one give a hint. It's you should try to organize things so that even you want to do maybe exhaustive search, you will be able to do it in a systematic way. So that will help us. For example, the final question, question 10, also maybe the third question, the balance system. So if you can organize things systematically, then it will become easier. All right. I will give you hints. For homework 5, I will give you hints gradually. So for some part, I think I will give you hints. All right. That's your question. Oh, sorry. This is just on that teaching evaluation. So when I finish, I will let perfectly know. Okay. Okay. So yeah, after 5 minutes. So what can we do? How can we do this? So let's see. So what we are going to do, say, consider n equals 3. So we need length 8. We need a string of length 8. All right. When we arrange them cyclically, then we get good property. So what we do is construct a diagram. whose vertices are string of length 2. So we have 4 different nodes. All right. Now I add an edge from U to V. If last bit is same as first bit of the node Y. I call it last bit of U equal first bit of V. I add an edge from U to V. So that's how I construct graph. So here I will have an edge, and this edge will be labeled the last bit of V. So here will be labeled by 1. All right. So this one we have a loop. 0, 0, because 0, 0, 0, 0. So this one is same as this one. And this one will be labeled by 0. All right. So we'll construct a diagram in this session. So this one has only 2 edges goes out because these two start with 1. So only goes here. Now the other one will go to this one and this one. This one will be labeled by 1. This one labeled by 0. If the last one is 0. All right. So similarly, this one, 1, 0 goes here, labeled by 0. 1, 0 goes here. Here labeled by 1. Last one is 1. All right. Now finally for this node, 1, 1 is to go to 1, 0, labeled by 0, and 1, 1 go to instead. All right. So that's the graph we construct. What can we say about this graph? It's a connected graph and it's Aurelian. This one is Aurelian. Actually, each has exactly degree 2 go out, degree 2 coming in. It's Aurelian graph. So what we have is the Aurelian tool. So this one has the Euler tool. All right. So what we do is find the Aurelian tool. For example, we can do this. I have to go like this one. Now I have a choice. It does not matter. If you want, we can go like this. All right. So that's one of our tool. Then I construct this string according to the Euler tool. Use labels on the edge in this fashion. So what happens is 0, so 0. Let me arrange it in linear fashion. 0, 0, then 1, 1. So I use this one, 0, 1, 1, 1, 0. Let's see. 0, 0, 1, 0, 0, 1. I missed the one, sorry. 0, one more one. 0, 0, 1. Okay. 0, 1, 1, 1. Oh, okay. Okay. So I did not miss it. 0, 0. Yes, that's it. Okay. 8. Okay. So that's our answer. You can check by yourself that if you take any three sections of this code are different. So that's why we can construct such a sequence. I think I can stop now because perfect here to do a teaching evaluation. I believe all of you have received emails. So please fill the form. That's time for revenge. Okay. So that's time for revenge. If you okay. I will leave, so let you do it. Perfect. I'm done. So I leave it to you. Hi, Perfect. Can you hear me? Okay, I have to find you in order to unmute you. I have to find your name first. Okay, I have to find your name first. Okay. Maybe I mute everyone. Unmute everyone first. Maybe. Sorry. Let me see. I don't see your login name, but yeah, yeah. It's